And let us go to the next talk. So now will be Kuptsov is here.
Yes, I'm
Uh,
here.
so please show your presentation.
Just a moment. Okay.
Okay.
Okay, I'm going to talk about an instant Lyapunov exponent. Lyapunov exponents is a very wide known tool for analysis chaotic attractors, and they are defined on infinite time. And I'm going to tell you about the other side of timeline. We are going to consider uh, exponents related to the present moment, not average somehow. So, first of all, I will briefly remind you about the basic ideas of computation of Lyapunov exponents. Also, we will need so-called covariant Lyapunov vectors. I will give you a brief idea what is it. Then I will show you how to compute these instant Lyapunov exponents. And finally, I'll give you two examples. How can we use them? What information can be extracted using these tools? And I think it is important to note that everything I'm going to tell you is about the numerical analysis. Well, key ideas of Lyapunov analysis. Uh, this is the trajectory. The green line is the trajectory, and the trajectory in general can have a contracted manifold. Uh, every trajectories on this approaches the reference trajectory. Expanding manifolds if we have a chaotic behavior, and neutral manifold if we consider a flow system, the system with a continuous time. And if we try to characterize behavior of vector of trajectories within these manifolds, we arrive to idea of Lyapunov exponents and covariant Lyapunov vectors. Covariant Lyapunov vectors are tangent bases for this manifold. They are not non-orthogonal to each other. They can change mutual angles along a trajectory, and they are defined in a tangent space. And if we consider the original phase space, then these vectors will be tangent for these manifolds. And Lyapunov exponents describe how these vectors grow asymptotically. Since these vectors are defined in a tangent space, their growth asymptotically is exponential, and standard classical well-known Lyapunov exponents are their average exponential growth rates. So we have positive Lyapunov exponents. If we have them, then we have a chaotic behavior. If a system have continuous time, we have zero Lyapunov exponent. Maybe we have more than one zero Lyapunov exponent in certain cases. And always there are several negative Lyapunov exponents. The total number of these exponents equal to the phase space dimension. Now I'm going to tell you briefly about the procedure of computation of Lyapunov exponents, because it will be important for definition of instant Lyapunov exponents. So we have a dynamical system. This is a vector. This is ordinary differential equation. And we need to construct a variation equation for it. This is a Jacobian matrix computed for this nonlinear function. We will call a propagator a linear operator that maps solution of variational equation from the time moment t1 to the time moment t2. Uh, Actually, this function is defined by Jacobian matrix, of course. And, and in numerical computation, this propagator is just the solving of our variation equation on a time interval from t1 to t2. Standard algorithm for Lyapunov exponents works like this. We have key orthogonal vectors. A key is a number of Lyapunov exponents that we want to compute. Key must be less or equal to the full phase space dimension, of course. So we initialize key vectors, and then we solve our variational equation on the time interval. Original vectors are mutually orthogonal. Then we solve our variational equation, which is denoted here as an action of this propagator. So we have some metrics, and with this we then need to orthogonalize this matrix. It means that we need to compute so-called QR decomposition. QR decomposition is defined for almost every matrix, and it represents this matrix as a product of orthogonal matrix and upper triangular matrix. Then we take this new orthogonal matrix Q and perform a new iteration, find new solution and new orthogonalization, and so on. We can always find a matrix Q in a way that diagonal of this upper triangular matrix will be positive. So because this diagonal is important for us. So when we perform this iteration, we need to extract this diagonal of matrix R and collect their logarithms. Because when we collect their logarithm, then we average them along a very long trajectory, and then we obtain a numerical approximation of a Lyapunov exponent. The formal equation is written here. So we average these logarithms of diagonal elements of R. The further slides explains the procedure of computation of covariant Lyapunov vectors, but this topic isn't new, it's just a review, and I think I can skip them to save time. I just have them just for the rain case. So we skip the procedure of computation of covariant vectors, but in general, the idea is following. We need to perform the mentioned procedure forward in time. This is this procedure. We perform iterations of our variation equation, then perform orthogonalization, and now we collect these matrices Q along the trajectory. Then we go far in future and then return back and perform backward in time iteration using so-called adjoint propagator. In the simplest case is an iteration with a transposed Jacobian matrix. And we go back, we need to collect these new matrices Q, and then we combine matrices QB obtained on a forward pass and QF obtained on a backward pass, and obtain these matrices P, and then we can extract covariant vectors from this matrix. I'm sorry, I will omit the very much details about it. So now we are ready to talk about local Lyapunov exponents. What are local Lyapunov exponents? These are the exponents. These are the parts of Lyapunov exponent computed on a short time interval. If we consider our general Lyapunov exponent, this is the averaging of finite time Lyapunov exponent. This expression is the thing that we are talking about. So, finite time Lyapunov exponent can be defined like this. So this is just the logarithm of this diagonal element of matrix R computed along the computation. Sometimes these exponents are used for analysis. Also, we can consider their distribution, but I'm going to go a bit further with them. Just a little remark. When we consider a standard Lyapunov exponents computed for infinitely large trajectory, we can say that each exponent characterize expanding or contracting properties in a phase space along its own direction. But if we have only finite time Lyapunov exponent computed uh, like here, using the standard algorithm for Lyapunov exponents, then there is no sense to consider them separately, because they have meaning only cumulatively in sums. The first finite time Lyapunov exponent characterize local growth or contraction or decay of a one-dimensional object, a vector. Sum of two first finite time Lyapunov exponent describe a growth of typical two-dimensional object, um, square, so to say, circle, and so on. And so on. If we have three finite time Lyapunov exponents, they characterize growth rate of volumes. But the third or the second finite time Lyapunov exponent have no meaning separately, only inside the cumulative sums. So this is just a remark. Now we consider a bit different sorts of finite time Lyapunov exponent. When we have covariant Lyapunov vectors, if you remember, I started my talk with this explanation that covariant vectors describes expanding or contracting manifolds. So we can consider their local growth or decay, and their local or decay will describe local expanding or contracting properties in certain directions. So the principal difference of finite time Lyapunov exponents is that they have meaning separately. First, second, and so on describes their own direction in a phase space around a trajectory. So finite time covariant Lyapunov exponents, this abbreviation means finite time covariant Lyapunov exponents, are defined as a growth rate of covariant vectors on a finite time intervals. Well, and now I'm going to talk about instant Lyapunov exponents. When we deal with a finite time Lyapunov exponent, the question is what time interval is appropriate. Usually we take it randomly, but it is not so solid. We need some solid ground for the consideration. So, and it is reasonable to consider two asymptotic cases. We can consider finite time Lyapunov exponent computed on very large time intervals, and this is a special story, also interesting. And also we can consider finite time Lyapunov exponent on time interval that tends to zero. And that's what I'm going to define now. It is very obvious definition. Uh, instant Lyapunov exponent, Lyapunov exponent defined for the forward in time procedure. Backward Lyapunov exponents means it's very strange notation. Backward here is about the origin of the computation in a far past. So backward mean going forward in future, and forward in this notation mean going backward along the trajectory. So backward means normal in this situation. Well, the definition is very simple. We are going to define finite time Lyapunov exponent in such a way that the integral from t1 to t2 average along this interval will be equal to our finite time Lyapunov exponent. So now we will see how can we compute these values. By definition, we have the following relation: sum of n first finite time Lyapunov exponents describe how n-dimensional volumes grow or decay along this interval. So we can write this equation. Now I'm going to substitute this value here, and then we have this equation. Now we need to extract this value from this integral. For this purpose, we will consider t1 as a constant and t2 as a variable, and find the derivative on this. The result is here. Then we need to recall that volume of an n-dimensional object in a phase space will be exactly equal to the product of the diagonal element of matrix R. Of course, I need to prove it. This is already proved, not by me, and I just will not take your time to reproduce this proof. It's very simple. So we just use it. If we have matrices R along the procedure of computation of usual Lyapunov exponents, and product of their diagonal elements equals to n-dimensional volumes of n-dimensional objects. So we substitute this volume by this product and go here. And now we have the following relation for instant Lyapunov exponents. So we need to find somehow the relation of time derivative of RII divided by RII. I repeat once more, these are diagonal elements of matrix R. How can we find them? Consider variation equation in a matrix form. This is it. V, capital V, is a matrix of some tangent vectors. Just a matrix without any special properties, and we can perform its QR decomposition and then substitute it here. Then we find the derivative and then perform some algebra to extract this relation at the last part of this equation. So we just multiply this equation by inverse R, then multiply by the transposed Q. I will remind you that Q is an orthogonal matrix. So we have this relation. And then we need to understand the property of this second term. This matrix has a special structure. Consider the identity. Because Q is an orthogonal matrix, we have this identity. And when we find its derivative by time, we will see that product of the transposed Q and derivative of Q is a skew-symmetric matrix due to this property. It means that its diagonal elements all zeros. So let's return to our relations. We have this equation, and within this equation, we know that if we consider its diagonal elements, we will not have this term because this term has zeros on the diagonal. So it means that we can find this relation as a diagonal elements of this term. When we write it explicitly, we have an equation for instant Lyapunov exponent defined for vectors computed along the standard Lyapunov exponent procedure. Sometimes this vector Q are called Gram-Schmidt vectors. And again, these instant exponents, Lyapunov exponents, have meaning only in cumulatively. Similar to their average form, these values have meaning only in sums. First one, sum of first two, and so on. Let's now define similar instant Lyapunov exponents on covariant vectors. We have this is the finite time Lyapunov exponent computed on covariant vectors, on covariant vector I, and here is the definition. We require that this instant Lyapunov exponent will satisfy this relation. But also we know that finite time Lyapunov exponent satisfy this relation. It by definition describes how covariant vector I grows on the time interval from t1 to t2. So we consider these two equations, these two parts, the two expressions, then find the derivative on t2. This is here. Then some transformation sufficiently obvious. And finally, after not so complicated transformation, we have this equation. This equation is for instant Lyapunov exponents computed for covariant vector. So just 2 words again, what we obtain and how can we compute them. Step back to see at this equation. How can we have this instant Lyapunov exponent? We need to perform a standard procedure for Lyapunov exponent. Everybody knows how to do it. Most of people knows this. We iterate this procedure, but now we not only collect diagonal elements of matrices R, but also we consider vectors Q. And at each step, we take vectors Q and computes this quadratic form with the Jacobian matrix. The result will be instant Lyapunov exponent, as you can see from this equation. And here the situation is a bit more complicated. First of all, we need to compute covariant Lyapunov vectors for time moments that we consider. And then when we know them, we need to compute this quadratic form with the covariant vectors. Well, and now 2 examples. What we how can we use these tools in combination with another known tools? First example is about analysis of pseudo-hyperbolic attractors.
Pavel, may I ask you a question?
Yes.
Pavel,
Yes.
what does mean J matrix?
Jacobian.
Ah,
It's a
okay,
Jacobian
thank
matrix.
you. Thank you.
This is the definition of a pseudo-hyperbolic attractors. I have taken it from this review in paper. So I'm going to check this list of properties directly using numerical computation. The first point is that tangent space is a direct sum of two subspaces. If we have a pseudo-hyperbolic attractor, its tangent space is a direct sum of two subspaces that never have tangencies with another, hyperbolically isolated subspace. The first subspace exponentially expands all volumes so that sum of the corresponding Lyapunov exponents is positive. The second one exponentially contracts all its vectors, so all corresponding Lyapunov exponents are negative. If the first one locally contracts something, its contraction is still weaker than contraction in the second subspace. So I'm going to check these properties directly, and I'm going to consider a Lorentz system. This system is a well-known example of pseudo-hyperbolic attractor. It has the following Lyapunov exponents. We see that sum of two exponents is positive, and the third one is negative. So the first subspace is two-dimensional, and the last subspace is one-dimensional. And we need to consider these subspaces. First question: does the first subspace expand all volumes? For this purpose, we compute finite time Lyapunov exponents and also instant Lyapunov exponents for comparison. And then we plot the distributions or histograms along the attractor of these values. We consider these values as cumulative values. So S1 is just the first exponent, S2 is sum of two exponents, S3 total sum of all exponents. And the interesting for us here is S2. S2 represents the expansion inside of the first subspace. What we see here, we see that locally the first subspace can be expanding or contraction, and contraction is even stronger than the expansion. I say locally. It can be locally in certain points, and there are many such points. And also we can see that if we consider finite time Lyapunov exponents on very short time intervals, they are very close to instant Lyapunov exponents. Here, actually, here you can see multiple curves. Some of the curves here is for instant exponents, and others are for finite time exponents, but computed on extremely small time intervals. Well, now we increase time interval, no instant Lyapunov exponents anymore, only finite time exponents, and we increase time interval to observe if the first property holds. So we see that when we increase sufficiently the time interval to sufficiently large value 10, then the first subspace start behave as expected. Only on sufficiently large time intervals, the first subspace expands all its volume as required by the definition of pseudo-hyperbolic attractor. Now we will check the property of the second subspace. Is the second subspace always contracting? Now, on this slide, we checked the expansion of volumes. For this purpose, we need Lyapunov exponents computed on the Gram-Schmidt vectors. But now we are going to check separated direction because the definition requires the contraction of all vectors, not volumes, but all separated vectors. For this purpose, we need finite time or instant Lyapunov exponent defined on covariant vectors. So when we check it, we see that, well, I see I have 10 minutes. We see that the second subspace contracts very good. L3, the green curve, represent the property of the third subspace, and we see that all the distribution is at the negative part of the plane, so it indeed contracts everything, even locally. And now the third property, that even if there is some local contraction within the first subspace, it will be weaker, not so strong as the contraction inside the second subspace. So for this purpose, we check instant Lyapunov exponent defined on covariant vectors. We find the smallest value of the exponent within the first subspace and compare it with the largest value within the second subspace. If this difference is positive, it means that the property holds. Positive value means that in any case, the first subspace contracts values not so strongly. So we see that we need to see at the orange curve. The orange curve is always positive, even for instant values, even locally for instant exponents. So we see that this property holds even locally. So the results of this analysis shows that only the first property is not hold locally. We need to consider sufficiently large time intervals, not extremely large, but noticeably large. So that was the first example. And now we consider quite different example. We will see what we can say about saddle node bifurcation of invariant tori. This is the system from our recent paper. This is a set of so-called Josephson junction. This is nanoscale device described by this set of equation. After rescaling, we have these dimensionless equations, and eta will be our parameters. Phi and q are dynamical variable. You can see that the system is totally 5-dimensional because we have 2-dimensional equation here for q. And the system typically demonstrates some sorts of quasi-periodicity. And we will not consider this system in more detail because this is not our topic. We will consider just a simple example. When we fix all parameters except eta 2, let's see at this panel. These two panels we will discuss later. Now we discuss the first one. When we fix parameters at certain values and change eta 2, we can observe so-called saddle node bifurcation of invariant tori. In the middle of this plot, in a gray area, we have, you can see here that the first and the second Lyapunov exponents, these are just ordinary Lyapunov exponent without some finite time tricks and so on, just ordinary Lyapunov exponents. And we can see that now in this gray area, only first two exponents are 0. It means that we have two frequency torus here. But if we go right or left from this area, we see that the third Lyapunov exponent becomes 0, 2. It means that we have three frequency torus here. So the description of this situation is here. We have some stable and some unstable tori, and at this point they match, and the three frequency torus appears. Well, that's what we have. Let's apply to this situation analysis using instant Lyapunov exponent computed for covariant vector. ICLE means instant covariant Lyapunov exponent. Well, what we do here, we plot how many times I will finish just
you need
a couple of minutes.
To leave 1 minute for questions.
I will almost finished. So the key idea is that when two torus merge, the structure of phase space changes, and it means that fluctuation of instant Lyapunov exponent along trajectory must change somehow. So we plot here, at this panel, we plot the largest value along the trajectory. We run along the trajectory, compute instant Lyapunov exponents, and take the largest one. And here we plot the smallest one. So we see that when we leave this area, when we leave the area of two-dimensional two-frequency torus, so we see that fluctuations of instant exponents extends. We see that the difference between the smallest and the largest value becomes higher. So, and it is interesting that this extension is related also to the first and the second exponents. The average value doesn't feel anything here because they are 0 and that's it, but their fluctuation feels this and indicates the bifurcation. So that's it. That's it. The result that I represented the concept of instant Lyapunov exponent. I have shown some example of using it. That's it. Thank you for your attention.
Thank you. Have anybody questions?
Yes, I would like to ask. It's Arkady Pikovsky speaking. My question is, we know that instant Lyapunov exponents and also finite time Lyapunov exponents are not invariant to the change of variables or to the choice of metrics. And therefore, it is not quite clear how their properties can be related to real properties of dynamical systems because of this non-invariance.
That's a very good question, I can say. Well, we need to think about it. I cannot answer. Of course, this question needs to be considered in details.
So, is there one more question? Only one is possible. So, let us thank again the speaker, Pavel Kuptsov. So,